So, hi and welcome everybody. Welcome back to the lecture of wireless security course. In today's lecture, we will be exclusively talking about wireless physical layer security. So this lecture is going to be an introduction to this domain. So basically, we will talk about the topics we are going to cover from and this is intended to be for beginner as well as for experts, so it's gonna teach you everything. And this is, as we know it, physical layer security is the transition from the application layer security, which is executed at the upper layers on the bit level, to the physical layer security, which is implemented on the signal level at the physical layer. So this is going to be a game changer, a paradigm shift in how security has been implemented so far. So up until now, we have talked about the security at the application layer, transport, network, and even MAC. And we said that all these security approaches are based on cryptography. And we even talked about some cryptography approaches that are used to secure your data against eavesdropping or spoofing or impersonation attacks or things like those. And we clearly mentioned that all these existing approaches are threatened in the future because hackers can be able to break them, especially when quantum computers become a reality. Uh, to be really clear with you, like there are many methods that are already existing and available in the research, in the literature, that can be used in order to crack many of the security algorithms. And these methods, all what these methods require and need is a super powerful computer to be able to speed up the decryption process, the hacking process. So, and we know many companies are working on producing super powerful computers. It's true that these computers are not in the hands of normal people. It's not in the hands of customers like you and me, but in who knows, those companies might have the access to super powerful computer that can execute millions of operations in milliseconds. And with this powerful computing resources, they can easily crack and hack any cryptography algorithm. So that's why we are under the risk of under the risk of hacking, under the risk of attacking, and we should be preparing for the future. So the data you have stored in your hard drive or the data you transmit to your friends or communicate over the internet, you might consider it secure now, but in the coming future, it's not going to be secure anymore. Hackers will be able to decrypt it, and therefore, countries around the world and institutions and security companies are racing and competing with each other. And it's like rivaling with each other in order to come up with solid, robust, alternative new security approaches that can solve the existing weaknesses in the currently deployed security algorithms. So this is the goal of this lecture, to introduce you to a new domain called wireless physical layer security that can have the promise, that can have the potential to replace the existing encryption-based methods. Now, I know that this might sound as a strong claim. You are saying, Hujam, you are saying that this can replace the existing encryption algorithms, but as you know, most everywhere, wherever we go, all the institutions, all companies, all the applications on the world are using normal cryptography approaches. So, I mean, and so far it has served us well. So what's the big deal? I mean, those are strong claims saying that physical layer security might have the potential to replace existing encryption-based algorithm. Yes, I understand the point and I understand the concern, because there are many papers in the literature that say the following fact, that physical layer security can be can be used as a complement to existing encryption-based approaches. So they don't claim that it's gonna replace, they say it's gonna be complement. Complement means it's just used to increase the security and make it harder for attackers to decrypt the data, to decrypt the encrypted messages we send, but they don't state that physical layer security can stand by its own as a robust algorithm that does not require encryption anymore. And this is what I'm going to show you in this lecture, because what's the point of using physical layer security on top of the other security approaches existing at the application, network, transport, and other layers? By doing so, you will be increasing the complexity of your system tremendously. And this is not going to be an effective solution in the current and the future coming wireless technologies that are specifically designed to serve millions of devices with low computational power resources and limitation in battery, in power consumption, in processing, in latency. So if you are gonna just use physical layer security as an additional add-on to the existing encryption methods, this is not gonna solve the problem at all. This is gonna just make it more complex. It's gonna make it more power hungry. It's gonna make it latency sensitive. It's gonna complicate things out. And this is not the solution that we are aspiring for. This is not the solution we are running after. This is not the, because we are dealing now with the Internet of Things era. We are dealing with devices that are limited in everything. So how are you gonna use public key cryptography, which is extremely complex and power hungry, to be implemented in an Internet of Things device whose battery is very limited? Just with a few transmissions for less than one year, the battery will run out and you will need to throw the device and replace it again. Would you consider this an effective solution? No, at all. This is not an effective solution. So the good target that we should put as an aim, as a goal, is to come up with algorithms that can stand alone by itself. I mean, you don't need to be dependent on the previous encryption methods, because they are power hungry. They are not good for future devices. There are many limitations for them. And in this lecture specifically, I'm gonna let you know about all these drawbacks and concerns and threats that exist as a result of using the conventional cryptography approaches, and what can we do to come up with solutions that can mitigate these problems. So the outline and the topics to be covered in this specific lectures and in this specific topic are going to be as follows. First, we'll give you a brief introduction about the importance and the motivation and background of this domain, exciting domain. And then after we give you the background and the motivation and the answer to the word why, I cannot motivate anybody to study or learn or listen to anything new if he doesn't understand the why. The why is so crucial, so important, so critical, that you understand why you are studying this, why you need to know about this, why the hell I should listen to this. So that's very critical, so that it can make you a sense of listening to what you are listening to, or feeling the drive and motivation to pursue studying a certain field. After we convince you, hopefully, with the why, and motivate you and inspire you and invoke you and let you on fire, we are going to discuss the system model of this exciting new domain, and the preliminaries and assumptions that we usually assume about this system model, and then we move on and talk about the secrecy notions and performance metrics, starting by secrecy notions. What are they? What are their meanings? What are the differences between them? Then we talk about the secrecy performance metrics that are used to measure the performance of the security algorithm you design and develop. And then after finishing with those, we will move on and talk about the security techniques and how we classify them into four main domains: secure channel coding design, channel-based adaptation and transmission, where we have time domain security, frequency domain security, space domain security, and even code and power. Then we will discuss the technique that's basically exploiting and utilizing the addition of artificially interfering signals, and those signals can be noise or jamming or interference or well-designed structured signals that can achieve certain purposes. And then under this category, we will give examples and explain techniques that operate and work in time domain, frequency domain, space domain, code domain, and power domain. After that, we'll talk about the fourth domain, which is called extraction of secret sequences from wireless channels. And the same with the previous domains, we will discuss also techniques that exploit the time domain of the signal itself, the frequency domain of the signal, and the space domain. Then finally, we'll explain, talk about and discuss some applications for this new domain, and then end up with challenges, recommendations, and the future directions, and what you can do next to catch up with this domain and be able to implement techniques that can replace cryptography approaches. So why wireless physical security? I believe we talked about it earlier, but this is just to repeat it one more time and emphasize things in a much better and clearer way. So wireless communication services are increasing rapidly day after day due to the spread in wireless devices, the spread in wireless technologies, and the spread in wireless applications. All of us are using their mobile phones, laptops, and those are always connected wirelessly to your network. So if you are always connected wirelessly to the network, to the access point, so it's very critical that you maintain the security of the connection. So the surge in wireless data transfer, everybody among us is continuously and regularly every day uses his internet to convey, generate information, send information, receive information. And this is increasing rapidly, as we can see, especially with the pandemic situation and COVID-19, where everybody is locked down in his home and working remotely. And even some politicians recently made the following statements that internet and the wireless connections and the internet access is the electricity of this era, which means you cannot do anything without it. It's what enables you to work, it what enables you to produce, it what enables you to communicate, it what enables you to get in touch with others without the need to even leaving your home or leaving your own home desk. It's an incredible, unbelievable era we are witnessing, and all the countries around the world are little by little transferring and moving to the digital era. So this puts more emphasis and more importance to securing the data being stored or transferred. So we call this data at rest, where your data is stored maybe in the cloud or in your hard drive or hard disk, or data you are communicating over the air, you are sending or receiving. Since wireless medium, as we mentioned, is becoming the dominant access for most of the internet-based services, then this needs to be secured, and there are serious security risks appear on the wireless signal because of their broadcast nature. And we explained the difference between wireless signals and wired, and we clearly stated that wireless is open to the air. So your signal in the air, anybody can listen to it, anybody can access it, anybody can jam it. And this make it severely vulnerable to security threats and attacks. And someone should come up with solutions that can countermeasure and overcome these problems. Users require confidential transmission for their generated wireless data, such as their important sensitive messages, calls, videos, financial transaction, whatever, and everything in between. As a matter of fact, strongly secure communication systems are needed and should be implemented without just relying on traditional cryptography key-based sharing approaches, because they have their own problems, which we are going to talk about in a second. The first problem that faces currently existing cryptography approaches is the key management, distribution, and maintenance processes. So as we know, if we want two nodes to communicate securely with each other, so the best security approach is to have common shared information, common shared key between the transmitter and receiver. So once they have this common shared key, they can use it to encrypt the messages and decrypt them securely. But what's the problem? The problem is in the management of these keys. Who should manage these keys? Who should we trust to manage these keys? Who's supposed to distribute them? And how are you gonna distribute them securely? And how are you going to maintain them? Would you allow these devices to keep using these keys forever? How often will you ask these devices to update these keys? So all these are questions that need to be addressed properly in order to be able to fulfill the requirements of an absolute secure environment. Otherwise, you will be under the threat of hacking and attacking. And this problem becomes more prominent, especially when you are in a large-scale, heterogeneous and decentralized wireless networks like Internet of Things networks and sensor networks and low-complexity devices. It makes the process even much more complex. So this is the first problem. The second problem, we all know that to increase the security, you need to increase the length of the key. Ultimately, the perfect case, the ideal case, is to have a key of length equal to the message itself, and whenever you generate a new message, you generate a new key for it. But with the currently existing sharing methods and distribution for keys, this is not going to be efficient at all. It will really suck and exhaust your resources in the network. So using longer key length, which is desirable to increase the confidentiality level, results in more waste of resources, which are needed for sharing, storing, and managing the keys properly. This is actually one of the other key killing problems with cryptography. If you want to, yeah, I know that in order to secure my data and make it really absolutely secure, I need to increase the key length. That's fine. I agree with you. I really love this solution. We all know it, and we all aim to reach that level of security where the key length is long enough so that it can be really, it can secure your communication strongly. But what's the catch here? What's the problem here? The problem that if you need your key length to be large, then you need to share it, which means that it's gonna take more bandwidth, more storage, more resources. So, and imagine I want to communicate a message of 10 gigabit per second. So I want to communicate a message of 10 giga. This means I need to share a key ahead of the time of 10 giga. So is this logical to do in currently deployed wireless networks? So what does this, what's the consequence of doing this? The first consequence is wasting the resources of your network, whether storage or bandwidth. transmission bandwidth, because in this case your throughput will automatically drop by half. Let's say you are excited, you are building a 5G network, your operator is going to allow the customers to enter and use it very soon, and all of a sudden, due to the implementation of such security approach, you were expecting to get an internet speed of 10 gigabit per second. You are now getting 5 gigabit per second. Not only this, but there will be severe signaling overhead while you are shaking hands, while you are exchanging messages, while you are sending extra information beside the data itself to make sure that the receiver can get the data correct and successfully without any problems. So this is really another challenge that exists with cryptography approaches. The third one is implementing security methods with Shannon perfect secrecy using one-time pad method, which requires secret key of length equal to the data itself, is impractical in today's data volume. This just confirms what I just mentioned about the key length. Now, the ultimate security, if you want to secure something ultimately, perfectly, which means there is no way a hacker can attack it or can get the message out of it, then you need to use one-time pad key, which is described by Shannon security papers that was published in 1949. So what does this mean? What does one-time pad method means? So it means that the length of the key should exactly be the same as the length of the message, and this key, you have to use it only once. You should not repeat it with some other messages at all. If you repeat it, you will be under the risk of analysis attacks. Now, again, repeat the requirement. You should use a key of length equal to the message itself, and this key should not be used one more time for any additional message you want to send. Two critical requirements. The key is very long and shouldn't be repeated, shouldn't be used one more time with any new messages the user generates. So this leaves us with this, that this is simply impractical to implement in current wireless systems, because we are not going to be able to communicate properly. We are not going to be communicating. We are not going to be sending our data and the content we generated from our applications properly with the left data rate after you use half of it for just sharing keys and signaling information. And where is the other problem also? This will cause delay for the transmission of your messages. Why is that? Because before you send any new message, you need to share a key of length equal to that message. So whenever anybody wants to send a message to anybody, he just calculates the length of that message and uses an algorithm that can generate random keys of length equal to the message and send this key to the receiver, make sure the receiver receives it correctly without any problems, handshake with the transmitter that everything is right, everything is correct, and then start sending your message. And when you want to send another message, then again share another key ahead of the time and wait for the receiver to acknowledge it and make sure that he received it successfully, and then send the next message, and so on. So do you think this is practical? Do you think this is efficient? This is what's required to ensure perfect secrecy. So now you will ask me, then what are they doing in the current wireless systems? What are they doing in the current secure systems? What they do is the following. Simply, they share one key, and this key is the length of this key is not the same as the message itself. Maximum it can be up until now, like if we are using advanced encryption algorithm, which is now the latest standard in security, and has a key of length like 512 to 256, but now the most secure one is 512, which means that you are sharing a key of length equal to 512 bits, and you keep using these keys with all the messages that you transmit between the transmitter and receiver, and sometimes the network updates it by generating another key, kind of changing your password after a few months of using it, which is ultimately not very secure because you are using the same key with many different messages you transmit to your receiver, and this makes it vulnerable and under the threat of analysis attacks. So this is not going to be very efficient. So what are the other problems? The other problem is related to quantum computing. The fast developments and advances in computing power devices reveal the fact that current secret key-based techniques, which are based on the assumption that the eavesdropper has limited computational power capabilities, can be cracked, can be hacked, no matter how much mathematically complex they are, especially when quantum computers and the quantum computing becomes a reality. This is the problem, guys. This is another key problem, another key challenge that the security field is facing. The security experts are trying to address. And this, I know, groups in the world trying to address this problem for Bitcoin, because Bitcoin is all about cryptography. And people are trying around the world to come up with cryptography approaches that are quantum computers resilient, which means even if you have a quantum computer, you cannot break your method. And those are killing drawbacks for the current encryption approaches. Aside from this, we have talked about the Internet of Things, but this is to emphasize the case. Just imagine a future where you have Internet of Things integrated in each and every sector and each and every domain in our industry and in our life, starting from healthcare, telemetry, retail, asset tracking, smart homes, smart agriculture, smart cities, water management, surveillance, smart building, fleet management, smart grid, electricity. Wherever you go, Internet of Things will become a major part of our life. So think of the Internet of Things as the internet itself that was invented in 1990. And imagine the huge impact that has made on the society right now. It's the electricity of this century. And imagine after 10 years from now what Internet of Things will make and what will it impact in the future. So it's going to be completely new era, new world, where every object has the capability to sense, actuate, send information, and communicate them, and even take control of things, starting from robotics, artificial intelligence, machine learning based machines, and so on and so forth. So it's going to radically change our life and change things and change everything, how it works. So the emergence of new wireless technologies like Internet of Things, massive machine type communication, 5G tactile internet, vehicular communication for autonomous driving like Tesla car and self-driving cars, remote surgery operation, instant control for sensitive Internet of Things devices, actuator, and drones, automatic control, and many of these applications that are alike will make current encryption-based methods unsustainable, and because they are not gonna fit the requirements of these applications. They are gonna make them unsuitable, since these kind of technologies naturally delay sensitive, power limited, and processing restricted. And I already explained to you the meaning of these things. And this is why encryption, specifically for your Internet of Things devices, is not gonna work. Anybody tells you why, tell him, let me ask you this question. How do you increase security? You increase security by increasing the key length. When you increase the key length, or you increase the complexity. When you increase the complexity, you increase power consumption, you increase latency and the processing. It becomes power hungry and the processing intense. So is this against the requirements of Internet of Things devices? He will say, yes, this is against the Internet of Things requirement. So then the security here is conflicting with the requirements of the Internet of Things core idea. So how can we overcome this? The ideal case is to just relieve the Internet of Things device from any extra processing for security. How are you going to do this? I don't just think of novel solutions that can overcome this problem. This problem I'm talking to you about is a challenge not to the security. It's a challenge to the whole world. We came up with the Internet of Things. Internet of Things is great, has so many advantages. It can help us in so many fields. It can be integrated with anything in our life. But what's the catch? What's the problem? If we don't secure properly, if we don't secure this properly, then everything in our life will be under the threat of attacks. And the attacks are gonna be severe, and it's gonna impact our life really ruthlessly and harshly. So what are we gonna do with this? Come up with a better solution for security. Internet of Things is useless if you cannot maintain its security. It's not gonna be a really wow factor in our life if you don't maintain its security. And the problem with the current encryption approaches, their nature, their characteristics are against the requirements of Internet of Things devices. And therefore, new solutions, new methods should be invented that can find a solution for this conflicting two requirements, the requirements of the Internet of Things device from one side and the requirements of security from the other side. Security, if you want to make it more secure, you need to make it more complex, which is against the requirements of Internet of Things device. Not only more complex, but also it will take more time. It will cause delay, and this is not good for delay-sensitive applications. I hope that you understand this point properly, because this is a good problem. I told you the other day that we like problems as engineers. We should be problems solvers, problem-seeking solvers. So whenever we have problems, you should be happy. You should not be like sad or afraid or this. Why? Now, one of you might ask, why we should be happy if we find the problems? Because when we find the problems, it means that we find opportunities. Opportunities means that if you can come up with a solution, then you have a business, which means you have established something solid in life that can generate jobs and income for so many employees in the future. So wherever you hear something people complain about, you shouldn't be complaining about. You should just think of how you can solve it and make a solution for it. This is the goal. So ultimately, what we see here is that users with sensitive applications like those related to financial and personal secret information can never compromise security. Nobody can disagree with this. Nobody can compromise security, especially considering the fact that we are heavily dependent on internet and data nowadays. Even if it becomes at the expense of slight degradation in other performance measures like throughput and reliability. Throughputs and reliability, we know that they are key performance metrics that we should always care about. especially reliability. So what we should now do if we want to secure our system, we should ensure also security. But sometimes security can reduce or degrade the performance metrics of these two key measures. So if I ask you, would you prefer to have a communication link of throughput equal to 10 gigabit per second and security and with ultimate security, with just enough security against some attacks but not all the attacks, or you have a link, a communication link of 9 gigabit per second but with ultimate security? So you reduce the throughput by 1 giga, but on the other hand you gave the customer ultimate security against all the threats, all the attacks. So which option would you choose, option 1 or option 2? So obviously you would choose option 2. I can tolerate some reduction in the throughput at the price of at the benefit actually of guaranteeing absolute security against any threats. Also, users are anticipated to even be willing and ready to pay extra charges just for the sake of completely ensuring the security of their important services. Thus, physical security as a service is expected to be one of the future killer applications of mobile service providers, where users, and specifically VIP users, can be charged a little bit more for providing them with strong, perfect, secure services. So all these factors and all these reasons and concerns are the key for the need for alternative solutions that are different from cryptography approaches. And in this course, in this lecture, in this topic, we are going to reveal some of the methods that are potential solutions for these problems. So thank you everybody for attending the lecture and listening to the exciting information about this topic. So we can stop here and continue next lecture with this topic.